Project on the foundation of physics called Assumptions of Physics, and I was invited to come here, and I'll give you an overview of the things that I want to try to do. There are three things that are sort of the main takeaway. As you probably know, that the current connection between math and physics is, let's say, suboptimal. Yes? I am using mine.
Okay, yeah.
Okay, let's do it like this then. Okay. So the connection between math and physics is suboptimal. You will have the experience of a mathematician to go and talk to physicists. You don't understand what they're talking about, and physicists have the same way, that they have the experience, that they talk to a mathematician and they don't understand what they're talking about, and all of this is not very compassionate. And the second takeaway is that I do believe that there is a way to, an approach that is still physically meaningful and mathematically precise, and this is what I'm going to be talking today. And the other thing is that new mathematics needs to be developed, and that's why I'm here. I'm trying to fishing for people that can help me do the things that I need to do. Okay, so a quick overview. So if you are familiar with the type of things that people do in the foundation of mathematics, it's setting up sort of the basic axioms that one would need, and it's kind of useful to understand exactly what are the consequences of each axiom. So the type of thing that you would do is that you say, okay, I have a base theory, which is the Zermelo-Fraenkel set theory, and then you pick the axiom of choice, and you want to understand the axiom of choice, and so you prove that from the axiom of choice you can get the Zoro's lemma, and then you say, okay, let's forget about the axiom of choice, let's assume ZF takes the Zoro's lemma, and then I can prove that I can go the other way. And so this type of things make you understand more a little bit what the axiom of choice is, because you have another way to reformulate it and get a little bit more insight. And this type of insight has been sort of captured by the quote from Friedman: when the theorem is derived from the right axioms, the axioms can be derived from the theorem, and this is sort of the basic insight that then sort of evolved into a field called reverse mathematics, in which they do these type of things in a very, very precise way. So I want to do something analogous, because if I want to have a physically meaningful and mathematically precise foundation for physics, again, it would be useful to understand exactly what mathematical property correspond to which physical requirement. So I'd like to have something like this, have some type of base theory, on top of which I have some mathematical relationship, and then find a physical assumption that is in some sense equivalent to that mathematical relationship, so that I can think as a physicist or I can think as a mathematician, and the two things actually map from one to the other. And again, the insight here is that when the math is derived from the right physical assumptions, then the physical assumptions can be derived from the math, because the two things are equivalent. And this is sort of the underlying idea, the underlying insight that allows us to do what we call reverse physics. So let me show you a little bit how that, what that looks like. So we start with the base theory, which is just the theory for classical states for one degree of freedom. The state is given by a pair of positional momentum, which as a mathematician you can think as a point in R square. And then you have something that gives you the count of states. So you have a set, and you have a measure that tells you how many states you have in that set. And that's mathematically is just going to be the integral of the QDP, or the integral of the volume form omega, which you can also think as a symplectic form, because it's a volume form. Okay, so we have this as a base theory. Okay, you have positional momentum and states. And then you say, okay, on top of this, I put Hamilton's equations. And Hamilton's equations are independent of the base theory, because you could evolve things in different ways. So you have Hamilton's equation, you want to understand, okay, well, that's nice mathematically, what do they mean physically? Well, one of the things that you can say is that you can rewrite them in this way. So you can have this dtq, dtp, which is sort of the flow of states in the state space. You can contract it with the two form omega, and you notice that that's actually the gradient of h. And so this is one way to formulate this set of these equations. And then you can also say, well, you can also go the other way. If I say that omega contracted to the flow is the exterior derivative is 0, then it means that it emits an exact form, and so on. And this is all very nice, and mathematically it's very interesting, but we haven't really understood what these things physically means anyway. So one of the things that you note is that this Hamilton's equation are asymplectomorphisms. So they're basically the set of equations that are there exactly when the omega is preserved. But since the integral of omega is the Liouville's measure, then this is exactly when the Liouville measure is conserved. Aha, now we can go and start making a physical interpretation of this, because this means exactly that the state count is conserved through time, right? Now we have a bridge, and we know exactly that these two things are the same. But what does it mean that the state count is conserved through time? If I have a set with 3 states, I will have a future set with 3 states. I'm mapping states 1 to 1. I have determinants and reversibility. So now I can go back and go forward, and all these statements are equivalent. But then you say, well, if it's reversible, I would expect it also to be thermodynamically reversible, which means I would expect the thermodynamic entropy to be conserved. And lo and behold, the thermodynamic entropy is the logarithm of the measure, and of course, if the logarithm of the measure is conserved, the measure is conserved, these two things are equivalent. So everything checks out. And then you say, well, if I have deterministic and reversible, well, it means that if I give you some information of the system at the beginning, I will give you the same information at the end. So there should be some type of conservation of entropy. And there will be behold, you find that this is exactly the same. Or you can also say, well, since information entropy is kind of uncertainty, there might be some relationship about uncertainty, and you find everything like that. So the point is that now you have a whole web of statements that are all equivalent to each other. Some of them are mathematical, some of them are physical, and you can understand the same relationship in a lot of different ways, and you get a lot more insight in what it is that you're doing, which are both mathematically precise and physically meaningful. Then you say, okay, this is all nice, so you're doing it in classical mechanics, can you do it in quantum mechanics? Okay, let's start with a base theory of quantum mechanics. If you're not familiar, the state is an element of the projective Hilbert space, and then you're going to have some probability of transitioning from one state to the other that is given by the Borel rule, which I'm already assuming normalized here, but it's basically coming from the inner product. And then you say, okay, I'm going to have a law of evolution here, which is going to be given by the Schrödinger equation. Okay, all of this, very nice. What do I do with this? Well, one of the things that you know is that the Schrödinger equation is essentially equivalent to unitary evolution. If you have a one-parameter family and so on, then you can go and find the generator of that one-parameter family, and you get the Schrödinger equation. So you have that, which is all very nice. And what you do with that physically? Well, you say, if it's a unitary evolution, then I'm preserving the inner product. And if I'm preserving the inner product, it means that I have the initial state if and only if the evolved state is going to match. So if I have the two states at the beginning are equal, or if and only if the two states at the end match. Well, then it means that you have a bijective map between state and probability, and it means that you have determinants and reversibility. And you say, okay, if I have determinants and reversibility, I would expect the information entropy to be conserved. And so you think, that should be equivalent. And lo and behold, this is the von Neumann entropy, and under unitary evolution, the information entropy is conserved, the von Neumann entropy is conserved, if and only if. So you can go back and forth. And then you can go and find everything and so on, right? So this is the type of things that I think are useful to do, sort of to get a precise understanding of what it is. And what is interesting here is that in both cases, the law of evolution is given by the same physical assumption. So the underlying base theory in the math has changed, but the idea of deterministic reversibility is the same. So this is kind of tells you that sometimes physical assumptions, physical ideas are more powerful than the specific mathematics in which you are realizing them. And so you start thinking, is there a more general base theory in which we can define and prove the correspondence? I'd like to have a base theory in which I say, oh, I have some state, and I have some entropy defined by some state. Can I prove some type of generalized Hamilton equation, and all these question marks means I have no idea what these things are, is such that if I assume deterministic reversibility in this general base theory, I will have this general equation that in classical mechanics reduces to classical Hamiltonian mechanics, and in quantum mechanics reduces to the Schrödinger equation. So these are the things that I like to do, sort of generalized things, but guided by physical intuition and physical principle. And to be able to do that, I need to define this space theory. So what are the basic axioms that I should put for a base theory? And this is what I need to study, right? I need to study the mapping between the physical world, which is necessarily an informal system. Like if I describe a physical experiment, you're never going to be doing it precisely in some kind of formal language. And then there's going to be a mathematical representation of what are the objects of the physical world. And so we have to understand how does this mapping work, and what are the standards of rigor and desirable table in this mapping. And this is exactly what we don't have right now, and this is where things get lost in translation, and yes, things become a mess. So this is basically how the thing works, is that physical objects are always fuzzy. They're difficult to pin down because there are interaction with other things and so on. So a lot of the time what you do, you make idealization. So you pretend that the system is deterministic, irreversible, that it's isolated, even though no system is really isolated, it's pretend. And so you make this nice, crisp idealization that then you map to the mathematical world. And then there are going to be some things that are either too hard or doesn't really even, I can say, it's not even useful to formalize. Just leave them in the informal world and put in the formal world only the things that are really important, that are going to give you the most bang for the buck. So this is what you would like to do, and you would like to have the map such that, again, you can go back and forth, you start with only physical things, we go to mathematically well-defined things, and you can go back and forth. And these are the type of things that you don't do right now. And what we realize that if you do that, if you find the set of objects that are mapped correctly, what happens is that the physical definition maps to the mathematical definition. Like you can't do it any other way. If you find the correct objects on each side, then it's going to have the properties of those mathematical objects are going to be properties that map something to the physical world. And so the insight here is that when the physical objects are mapped to the right mathematical objects, the physical specification actually map to the mathematical definition. And so you can just concentrate on that. You concentrate on what is it that you're modeling, and then translate those things into mathematical definition. And how do you do that? Well, let's take an example. Let's say that we are describing ensembles, and we want to give an axiom, which we call the axiom of mixture, that says that the statistical mixture of two ensembles is an ensemble. And this is something very intuitive that makes sense to any physicist and engineer. You can just take it as something given. And of course, if you go to a mathematician and says, okay, what is an ensemble? This is not precise. And so what you do is you want to extend this definition without formally an ensemble space is equipped with an operation plus called the mixing, noted in the fixed notation, that has all these bunch of properties. And now this is a formal definition that a mathematician can look at that and understand it. Oh, this is just the ability to create convex mixtures. You have a convex space there. And now you have two definitions, which is worse than having one definition, because now which one does it count? So what you need to do is to have a justification. Something that you know what is it that you are describing intuitively, and then you go painstakingly to go and show that if you are taking the informal intuitive requirement to be true, then the formal definition and the formal requirement follows. So, for example, you say that the axiom captures the ability to create a mixtures merely by selecting between the output of different processes. Let A1 and D2 be two ensembles that represent the output of different processes P1 and P2. Let A selector as P, and so on. So this is what you have the pictures here. You have the two processes here, and they're getting mixed, and that's the output that you get. And you want to do that for all the different properties. So, for example, if P equals 1, the output of P will always be the output of P1. This justifies the identity of the identity property, which is the second one. Right? So these are not proofs, right? Because they are linking informal objects to formal objects. Maybe in the 1700s these were considered proof, but not with the current standard of rigor. But we need this type of things. And they have to stay in the middle. And I can tell you that being forced to do these things, you really have to go through all your mental model and make sure that it's correct. And sometimes you find things, oh, actually, why am I assuming that? And so on. And then brings up all the hidden assumptions. So, okay, so basically, if you do this, then there is no question of what the math describes. It's not that you start with some math and then you try to interpret it, or no, you know what it is that you have, because the properties are justifies and are consequences of what the model describes. So every proof now can be reread as sort of reinterpreted through this justification, and so the math describes and only describes a physically meaningful concept, and that's why I call it physical mathematics, because it's mathematics, but it's representing physical things. And so the idea would be to redo all the physics and all the math that we need in physics by doing this. And this is why it's a big program, and I need help because, Lord, I need help. So we have methodology, and now we need to understand, okay, what are the most basic objects of this thing, right? In sets, you use that. In categories, you use category. What are the building blocks of this? And so this is where you need principles that sort of guide what is it that you're trying to describe, and you have the principle of scientific objectivity that tells us that science is universal, non-contradictory, and evidence-based, which is science is about statements that are associated to experimental tests. So we have two logics. One, whether the statement is true or false, and that's two-value logic. And then we have tests, and tests may succeed, may fail, but it can also not terminate. And so we have a three-value logic, and we have special statements that are verifiable, which means that if they're true, then the test succeeds in finite time, and if the test succeeds in finite time, the statement is true, so that we don't have that problem. And it turns out that this is enough to sort of start characterizing a lot of things. So we are going to have two sets of axioms. One are the axiom of logic that sort of gets us to the Boolean algebra, and if you look at them closely, you're going to see that there is an informal part and a formal part, and then of course there is a justification, which I'm not putting here. But the point is that these axioms are chosen not because of trendy mathematical techniques. They're chosen because I can make the justification easy and clean, because that's what we need. Then from those, we want to recover as much as possible mathematical structures that are already known, such that I can give them to mathematicians, says, go and study what is it that I need. Oh, okay, I can have all these theorems that are good. So we have the axiom of logics that basically gives us a Boolean algebra, the axiom of verifiability that gives us this more intuitionist frame locale type of thing. And what you do with this, you can prove that essentially everything that you do in physics, all the objects that have to be physically well-defined are points in a T0 second-countable topological space where the interior corresponds to the termination condition of the test, the exterior corresponds to the non-termination, the false, the failure of the test, and the boundary corresponds to the undefined, the non-termination. And you can go and reread a lot of things, and you will see that there is a very close map. And this is what basically gave me confidence that this program is even doable, because you can go and find all these correspondence, which of course we have no time to talk about. So I need now to go and create new things, and this is where I will need most of the help. I need essentially to describe states and processes. And again, I have this second, the principle of scientific reproducibility that tells us that the scientific laws describe a relationship that can always be experimentally reproduced. So scientific laws are always something, not something about, oh, at Friday 3 a.m. this happened, but it's whenever I do this, I will have that, right? So it's not a relationship between two elements, but it's a relation to a collection of elements so that it can be reproduced with a preparation procedure and measurement procedure. And so the idea is to study what is the basic set of requirements that you need to be able to properly describe the ensembles mathematically and see where you get. So these are the three sort of set of actions that we have right now. I think we're missing a third. One is going to be, I need to have experimental verifiability, so I'm going to have a topology that is T0 second countable. I will need to be able to mix things as we saw before, so I'm going to have a convex structure, and that convex structure seems to me that it's really responsible to all the other linear structure in physics. They're all coming from here. And then I will have this idea of an ensemble variability. The ensemble is a collection. Things can be different in that ensemble, and the entropy actually is the thing that characterizes that. And that's basically responsible to all the geometric structure. There is a fourth one that I think has to do with the sort of the Lie algebra of Poisson brackets and commutator that I still don't know. But first, it's a good idea to understand how much you can get from these three before adding new things. Okay, so what can you do with this? Well, already we can do some things. You can define this maximal entropy increase in the entropy bound, and you can recover that has to be the Shannon entropy for all physical theory, which is nice. So the proof doesn't know if you're using classical mechanics or quantum mechanics. You just get the Shannon entropy, which is nice. And the proof is just like a page and a half. So this is where you know that you have good axioms, because the proofs become short and nice. You can define a sort of distance function by basically saying, I have two ensembles, I mix them together. how much does the entropy go up? If it doesn't go up, those two ensembles are the same. If it goes up maximally, we define these to be orthogonal because they're mutually exclusive, and you recover orthogonality in both classical mechanics and quantum mechanics, which is nice. Again, you can develop concepts with very little input that actually work well in both things. Since the entropy has to be strictly concave, if you stick a minus sign in front of the Hessian, you basically get what is a metric tensor, and this actually recovers the Fisher-Rao metric for both classical mechanics and quantum mechanics, and there are a lot of things that I like to do. And then one other thing that you can do is sort of have some non-additive generalization of probability and of the Liouville measure, and this is where I'd really like to have some help, also because the standard tools that we have in non-additive measure theory don't seem to work. We need something else. And so this means that I have a lot of open problems. So, for example, I'm interested in topological convex spaces, but there are a lot of work on topological vector spaces. So what are things that in topological vector spaces hold in convex spaces and what not? So can we show that the entropy induces the metric that is inducing the topology or not? Can we prove a continuous embedding of our space in a topological vector space? There are some issues there I've been trying to for months and I don't. Anyway, so there are other things that the point is that I'm actually looking for people to help me. And then the whole goal would be that also field theories should be able to fit in here. So how do we put probability measures on function spaces and then have a Shannon entropy-like entropy function of those things? I have no idea how to do that, and that's something that needs to be understood. Okay, so in conclusion, to wrap up, as I said before, the current connection between math and physics is kind of suboptimal. Physicists typically ignore all the hard problems, and mathematicians cannot know which choices in the underlying frameworks are physically significant and which aren't. I found that economists have more of a sense of that than physicists, which is scary. And a physically meaningful and mathematically precise approach, I think, exists. And reverse physics is basically what allows us to understand what role each mathematical structure is playing in a physical theory. And without that, we are not going to do very far. And this idea of physical mathematics allows us to design mathematical structures that are physically justified and therefore map perfectly to the physics. And I do think that new mathematics need to be developed, and we have a number of mathematical questions, and we're actively looking for people that are interested. So if you guys are not interested, but you know somebody who could be interested, just set in my way. And to learn more, we have a project website, assumptionsopphysics.org. Everything that we do is in a book. I'm about to make a new edition where it talks about these ensemble spaces and all the open problems, and you can look at that. I have 2 YouTube channels where I talk about these things, and everything that I do is in GitHub, so you can go and look at all my history of commits and see all the idiotic things that I said in the past. Thank you.
Thank you, Gabriele. Yeah, let's take a couple of quick questions while the next speaker gets ready. Yeah, Jeremy.
So maybe this is going to sound kind of like flippant and like absurd, but like why the real numbers? If you're going to start, if you're going to have this theory.
So for real number, you know that I have that part of the topology. I have a set of necessary sufficient conditions for which, if I'm trying to do a measurement scale, essentially, I have references, and I can say something is before the reference and something is after a reference, and those two things are going to be some verifiable statements. And then you ask, what is the sort of necessary sufficient condition for a set of statements to give you real numbers? And we have identified those, and those are highly idealized, so you basically are going to say that at some point those assumptions are not going to hold and you need something else. I have no idea what it is, but if you want to talk, we can discuss it.
It's a very interesting question. It's like, what physical assumptions are pinning down the real numbers in our physical theory?
Yeah, so I tried to present that, and my talk was rejected because it was not mathematically sophisticated, so this is where I live.
Yeah, we're trying to be compassionate, right? So yes.